to stay off of video to save bandwidth since I'm doing a live presentation. Just wanted to say hello to everyone first. And let me share my screen. Let's see the code. No, that's not what I wanted to show. Okay, people can see my screen. I'm assuming yes.
Yes,
okay.
Yep, we can see that.
Okay, good. So I'm here to talk about the results of our Medical Field Radiology Grant Challenge project that has been running for some time. And hopefully this will give you a sense of what does it take to pull off a grant challenge project that runs for several years and aims for a very high goal. And in this particular case, it was to essentially, although we didn't call it the Turing test at that time, but in the end, what we ended up building is something that produced a capability that was virtually indistinguishable, at least for the test cases we tried. So before I go on, I just wanted to acknowledge my team. This comes with the truly interdisciplinary effort from radiologists, the majority of the involvement from clinicians, but from the radiologist community, both internal and external radiologists around the country. And my team members who are medical imaging researchers. Some of you may be already familiar with these folks who regularly publish at MICI. So let's look at what's the grand challenge. The grand challenge we took on, we started back in 2013, 2014 timeframe, was to look at developing capabilities for assisting radiologists and making good cognitive clinical assistance. Now, this concept has now been adopted and is already in many products. Even our own Watson Health imaging business has utilized the technology from our group. But the challenge that we took on was to build a capability that was provably good. And in this particular case, doing a full preliminary read of a modality directly from images to report. And that was the grand challenges we took. Now, in this particular case, the focus was on chest X-rays. So you may ask why chest X-rays? And I think enough work is now happening in chest X-rays. But back when we started the challenge itself, this was not as popular. But from the point of view of preliminary reads for doing this, these are, even though this is a common modality, they are also one of the hardest to interpret because of the low resolution in the imaging and the cognitive biases. So if you were to look at these two and figure out which of them is actually a nodule, this can be difficult for machines. So in such sense, the idea being that if you could produce a preliminary read, which means going from an image such as this to directly a report, this could potentially assist in expediting the clinical workflow as we go. So the way we envisage is that in future you may have read services that can intercept at any stage of your clinical workflow, from imaging, assisting the technologists to make sure that the imaging itself is of good quality, to ordering the work list of a radiologist so you can interpret them, the more urgent cases first, to actually skipping the dictation process itself, producing a preliminary report that the clinician can still correct and sign off. So we see this as a way of disrupting the current dictation-driven process if machines got good at producing high quality reports that reflect all the possible findings and flag as few incorrect findings. Now, just to give you the type of capability we reach, you can see a bit of a demo over here. I don't know if people are able to watch this video, but here's an image. You just feed it to the service, and the image is being analyzed and a report is being generated here. And you can do this by picking any of your images from your packs and submitting to this service and producing a report as such. So in the interest of time, let me move on to the rest of the deck. So you may say, why is this a grand challenge? So the first question that we have to answer is, if you're saying you're going to do a full preliminary read, you have to be able to cover as many findings as the radiologists do in a read. Then the question then comes back to how many findings are there. It turns out that this question has not been adequately answered, and the majority of the work since we started as well has also been only restricted to a small number of findings, like 14 findings or 20 findings and so on. But we don't have a good answer of how many findings are really there, and how can we be sure that we've completely characterized them. The second thing is you need to be able to be as accurate as radiologists, at least the entry level radiologists, in detecting the findings. But how can you be sure? What are the radiologist accuracies? Are there studies that actually document this? And so this itself was another problem that we had to face. The third was to actually look at, when you say you're describing the as good as an radiologist report, we need to be able to characterize the findings at the same level of granularity that we did see them. And here are some examples of actual sentences from reports. And you can see that there are fine-grained descriptions of findings that describe the laterality, the location, the severity, and so on. And if you were to look at the findings, and if you assume that there is going to be a large number of findings to cover, you still need to develop AI algorithms that have that kind of specificity and sensitivity, such that what is actually mentioned in the report is typically only a handful of findings, and we should be able to do that high level of selectivity as well. And overall, we need to be able to produce a report that is of adequate English language description and quality. So if you look at this, the problems to be addressed are both on the radiologist side and on the machine side, because as I mentioned, there isn't even a catalog of all the findings or a benchmark of what the ground truth would be that to compare against and so on. So there's a lot of work we had to do to develop the benchmarks, to develop the catalog of findings, and this is where the clinicians' involvement was pretty heavy. And then we also needed to develop machines with the capabilities to detect and characterize these findings. So if you look at a typical work involved in this, there is a lot and here's a few of these that one can, and many of you can relate to, have done one or more of these tasks. Obviously, it's not possible for me to go through all of them, so I'm going to touch on a few of these topics in a very brief way and leave some time if there are time for questions. So let's start with the first one, where, as I said, we had to first of all characterize how many findings are there. And as I said, most of the approaches have focused on the 14 findings that were initially released by the NIH dataset, and a subsequent labeling by Chexpert or Mimic or all have also kept to those. And some proprietary organizations have done a larger range of findings, but it's not possible to find them in the public literature that we can actually utilize labeled data sets. So our first task was to build a chest X-ray lexicon that allowed us to catalog these findings, and this is something that we subsequently utilized to our advantage. So for cataloging the findings, one would have to look at what is the radiologist process. So if you look at a radiologist process, the initial interpretation, first to see if the image itself is ready for interpretation, which is a technical assessment problem. Then we need to know whether it's an AP or a PA or a portable view, as it establishes some bias as to whether you are in an inpatient or in an outpatient setting. If you are in an inpatient setting, you have to detect if there are any tubes and lines and whether they are properly positioned, or there are any implanted devices or artifacts that need addressing. If you look at the anatomical abnormalities, you have to also detect all the major findings in major areas of the chest and any disease that is implied for that, and you finally generate a report. So this is typically a workflow of a radiologist and showing you the many types of findings that one need to detect. So this gave us the first hint to go ahead and try to catalog the findings as we go. So we collected a team of radiologists and used a process that was a combination of knowledge-driven and a data-driven process from actual mining of reports to develop the largest catalog of findings, as you can see from this chart. This work has been described in the AIMBE conference last year at the American Medical Informatics Association, and the technology itself is described in detail there, but at a very high level, we used a clinician in the loop process of mining radiology reports and having a reinforcement learning approach, be in the loop, utilizing word-to-vec representations for finding similar terms within radiology reports and having the clinicians accept or reject the terms as synonyms descriptions for the particular core disease characterization that we started with. So as a result of it, the lexicon that we developed has about 11,900 or so terms and about 237 lexical concepts, about 78 core findings and 26 clinical categories. Here is an example of the core findings, about 72 of them listed over here or so. And the details of these has been published in our JAMA paper last year in October issue, so you can also get more details on this day. So that is about the findings itself. The next step was to acquire data that was representative of multi-institutional data sets representing several demographics in the population and handling different prevalence distributions of these findings as such. So in terms of acquiring the data sets, we at this point, based on the access we had, we looked at data sets from NIH that were supplied without detailed labels like these. So we had to relabel some of these images, and about 14,000 of them we could relabel by reproducing reports out of them. The next was the MEMIC CXR dataset that is now in public, but at that time when we started, we were part of a consortium, and we got access to about 500,000 images from them, and the Indiana collection as we see. And we also kept aside a certain two sets of data for experimentation purposes that did not have an overlap with the training sets for the machines. And this included a data set from a completely different demographics from the hospitals in India. You can see the prevalence distributions of the various findings over here, and you can see that the comparison study data set that we said had quite a different prevalence distribution for testing. It's to test the robustness of our models. Okay, so we got the data set, but none of them came with labels nor the fine-grained descriptions that we wanted to generate. So our next process was to be able to actually automatically label these data sets. The manual labeling process that we first adopted for the NIH reports took about 4 months, and at about 36,000 images, considering different viewpoints, was what we could annotate. And since we had 1 million or so images to go, we said this is not going to scale. So we came up with an automatic labeling method that mined from reports. And I know a number of other approaches have taken automatic labeling approaches as well. So the way you will see them is many of them are machine learning driven or vocabulary driven. What our approach actually is a combination of machine learning, vocabulary, and language modeling, as we go through a bit of a description over here. The first approach that uses a vocabulary from the lexicon directly to to locate these findings can do a course level description of findings. And this one we have evaluated on many data sets, and we published this work last year, which shows that it has pretty good precision and recall on the collections that we have ground truth and tested from clinician ground truthing of these reports. In fact, if you look at the F1 scores comparisons for the findings, and the blue findings are those that are in published list of findings, but as we go, this is a distribution that shows that much larger coverage and also the kind of F scores we are able to maintain in comparison to the state of the art there. Again, this is available in our EMEA paper last year. So that only characterizes the coarse findings. So we would know pneumothorax, but we would not know which lung has pneumothorax or which portion of the lung has pneumothorax. So if you want to go to the fine-grained findings level, we actually have to do a further analysis to be able to characterize descriptions of these findings. So we actually came up with a catalog of what descriptions are actually found in reports. And you can see over here, laterality, location, size, and so on covered over there. So this leads to the next question. The first question of how many core findings we were able to answer by clinicians. But when you go to find finding, there are thousands of variants, hundreds of thousands of variants, and having clinicians go through this cataloging process would have taken us 10 more years. So we came up with an approach that actually tried to use language analysis techniques. So if you take a report such as this, which says clear lungs without evidence of pneumonia, we already know from our lexicon that pneumonia is a disease, lung is an anatomy, clear is a description of a finding, and there is also presence of negations. So utilizing this information and using an English language parser that was adapted for clinical vocabularies, which is called the ESG parser, that is behind the Watson technology, we were able to create a parse tree for this, and then use a dependency parse tree to actually group successive core findings and adjectives and modifiers that describe these findings together to produce findings from a single sentence. So a sentence like clear lungs without evidence of pneumonia would generate an anatomical finding, which is a negative finding in this particular case of a clear lung. And from the point of view of a disease, there is a finding of pneumonia, but it's also a negative evidence. And the pattern itself can be characterized in this four-part form as such. So, and here you can see over here from a single sentence, we can generate multiple findings as well in this particular context. So this work is again described in detail in our AIMBE paper last year, which won the Home of Honor Award for Best Paper. So from there, we can, starting from an image like this, if we could had a label of this type, it is relatively easy to generate a sentence that says left basal atelectasis. Similarly, if you had a detailed description of a finding of this type in a label form, it is possible to describe sentences of these types. We actually did an analysis of about 3,000 sentences from about 2,900 reports to see how accurate is our fine-grained descriptions. And as you can see over here, less than 4% error overall, and the majority of the errors were in the negation sense detection, which remains to be a challenging problem in text analytics. Okay, and when you do the full characterization, we can form a tree of this type, and you can see that this represents about 83% coverage of all fine-grained findings, and about 457 fine-grained patterns that we retain that gives a good span of the 100,000 or so findings that we found from about 220,000 reports as we go. Okay, so now we have labeled data sets describing fine-grained findings as discrete labels. So now the question was, how do we build models that are able to handle such large number of findings and still retain the quality of recognition? So in this particular case, we looked at building first specialized deep learning models, which we have published in literature, such as the tubes and lines classifier in MICAI, or the technical assessment model and SPI and so on. But the goal was to develop a general model that covered all the findings. So we, after experimenting with several different network architectures, we settled on an architecture that has a combination of many good features. One of them is a multi-scale representation of the image using feature pyramids drawn from pre-built networks. The other is a dilated block that allows us to represent higher levels of abstraction as we go through findings at different regions and expanding to multiple regions. And then a global square pooling or bilinear pooling that instead of shrinking as you know, in a convolutional operations, the sizes of the filters are such that the image size shrinks, and by the time you get to the flattening stage, you have a small vector compared to the raw sizes of images we look at. So this particular step, we did actually a global square pooling, which actually expanded the feature set before you did a dropout and then a dense classifier as such. The network details are also described in our JAMA paper, but this is the three-step operation we used for this purpose, and the details of the machine learning model configurations are given over here. So that gave rise to the machine learning model. We'll show you how that model performs when we get to the clinical studies section of it. So last step of the problem was to actually generate the report from such a model that described the findings as such. Now, this is where, as you know, there's a lot of work active going on in report generation by machines, and the predominant approach that is taken is a machine learning language-driven techniques. And in fact, you can see some representative work here. Typically, they start from images and try to generate labels. And from the labels, using any surrounding textual during training, use a language generation approach, variants of LSTM or RNN and so on to actually generate the report. So the report essentially is generated by language transformer type techniques, and it is seeded by image recognition from image findings. And there are variants of this, of course, but the general approach is that. And so one of the major issues with this is ensuring that the report is clinically correct, describes all relevant findings, and sounds reasonable as well. So those three problems are still outstanding as we go. So our approach to this was quite a different departure from these existing techniques. What we did was, first of all, try to describe the findings in a coarse way, such as elevated hemidiaphragm or cardiomegaly. So one model to characterize the coarse nature of findings, another model to characterize the fine-grained nature of findings, which for the same elevated hemidiaphragm will now say elevated right hemidiaphragm mild, which is the label itself, and then go from there directly to a sentence that says the right hemidiaphragm is mildly elevated. And so this uses a technique that is familiar to radiologists in the way they have pre-canned sentences coming from their dictation systems. However, instead of pre-canned sentences, we actually detect the relevant sentence based on the findings by creating a large database of sentences and using a document retrieval style approach as well. So the overall approach would be starting from a prior report. We create actually a database that extracts all the fine-grained labels through this automated labeling process to characterize fine-grained finding vectors. And from these vectors, we extract the sentences per FFL vector and reverse index to know which sentences were contributing to these vectors, and essentially create a ranked sentence database and a ranked report associated with this and during the database preparation step. Given any chest X-ray for during inference, you just take the report and learn the fine-grained labels from it using the model that we build, predict the fine-grained label vector, and then use this retrieval engine to actually retain the relevant sentences, and from there generate the report. Now, during the sentences, we also do some wordsmithing to make sure that the sentences are complete and so on as we go through. So the overall report generation system, therefore, is a fusion module that uses a coarse and a fine-grained labeler and a retrieval module that works off of a database. And you can see here some of the details of these in terms of the database preparation step. About 5,000 sentences are guiding the analysis of each of these findings report generation step as we go through. Now, how to measure that this is a good quality report is also difficult because most of the measures out there are based on lexical match or some weak semantic matches through scores such as BLUE or Meteor. However, to compare to other approaches, we had to stay with that methodology. But first, in terms of the detection of the findings itself, for coarse and fine, you can see that we have about weighted average AUCs of these. And you can see the depth at which we can now predict from an image findings such as moderate pleural effusion in the right lower lobe as well. And here are some ROC curves we got for the fine-grained descriptions of these findings. This work, by the way, has been described in MICI last year. So the automated report generation generates sentences of this type in comparison to the ground truth. And you can see that the finding is captured, but also described in an appropriate way. We tried to do a comparison with many other methods in terms of how the English language description and the sounds from this using the same scores that they use, such as blue score or the Meteor score or the Rouge score. And you can see that this is still the highest, I think, in terms of performance across the board for all the, even though the language generation methods are not the best way to assess our model, that is it still beats the state of the art as of last year. Now, of course, there'll be new approaches coming in this year, so we'll see how that goes. All right, so the last step is now, how do we know how good we are and how can we prove that we have reached a certain capability? So as I said, we needed to conduct clinical studies to measure the radiologist performances by, first of all, developing a ground truth data set that radiologists themselves could agree on is the right data set to evaluate them as well as machines. So in that sense, our evaluation process was split up into the radiologist communities, a set of community that developed the ground truth data set, and these are the senior radiologists who did a triple consensus ground truth generation process with adjudication. Then we had a radiologist committee that acted as the attendings, which are the senior radiologists that assist radiology residents and that assess, sorry, the radiologist residents. And then we had radiology residents as representatives of entry-level radiologists that we could compare to, and we use R3 residents as our comparison as such. Okay, so the type of studies we performed were first for normal and abnormal discrimination. How well does this come? And for on completely different demographic data sets. Then we did a comparison on discrete preliminary reads, followed by preliminary report quality Turing study as we go. Let me quickly go through these. So in the normal abnormal discrimination study, this was conducted at the Deccan Hospital. It's a 600-bed hospital and we basically collected a definition of normal patients in this case, for those that had no clinical follow-up after a chest X-ray was declared normal by their radiologists. And so in the retrospective phase, we collected data from them for evaluation. And in the prospective phase, we actually ran this normal abnormal discrimination surveys and had the clinicians themselves use it for several months to record the performance as we go. So the data set essentially had about the training data set came from our MAMIC and NIH collection that were auto-labeled by machines as normal or abnormal. And based on that training, we went back and used the radiologist reports that their clinicians at Deccan said were normal, abnormal to get to the classification. So from the ROC curve, you can see that if you pick a point on this ROC curve, we can essentially remove 1/3 of the normal images without missing a single abnormal case. And that tells you that there could be a good potential application for this for normal abnormal screening itself. And then in the precision recall curve also is showing you a high level of performance there. All right, so that was on the discrete normal abnormal discrimination. The next one is on discrete label comparisons, and the study was described in a JAMA paper last year. So there are 5 radiology residents that we compared to. These are R3 residents, about nearly 2,000 chest X-rays, giving about 400 chest X-rays per radiology residents. And then we did basically their individual radiologist performance, average radiologist performance as measured, and then the agreement with the machine reads from the CAPA scores and the average image-based precision and recall measurements. And there is a lot of detail in that paper that you can read, but you can see the AUCs per finding cataloged in here that shows that the sensitivity specificity numbers and the positive predictive values are roughly in similar ranges for machines. In fact, if you do a comparison of the ROC curves, you can see cases clearly where the machines are about the same. With the on the ROC curve, the radiologists are right on the ROC curve. But there are cases where the radiologists are better, and then there are cases where the machines are better as well. In fact, if you look at the average CAPA scores, you can see the variation is pretty close in many cases. But there are cases where the radiologists are much better, and we'll show you that. And then we also did the variation within residents. Also, there is comparison studies that show differences. Overall results that said that basically, this is a significant result from the discrete comparison study that said that there is no statistically significant difference in sensitivity, but the specificity wise with the machines were actually better, which was a bit of a surprise to us, since the number of false positives, as you know, for machines is quite large when you just do it purely as a machine learning model building exercise. But because we augmented this with the report generation and utilized the information about the average number of findings that are typically present, we were able to control the selectivity of the machine to be on par with the radiologist as such. So overall, this meant that they are roughly on a similar level of performance. And in fact, if you look at things where machines are similar, here are the findings that we found they were similar. And there are findings where the machines outperform the radiologist, and then And there are many cases where the radiologists outperform the machine, and these are the difficult findings associated with tubes and lines and their placements, as well as nodules and certain things that were also a little bit of a surprise as to why the machine missed it. So the last study is to bring this whole thing together to now the prime time testing in terms of how does the machine produce, are the reports produced by the machine good enough in quality that it's virtually indistinguishable from the radiologist reports. So to conduct this study, we actually had radiologists write reports for these same 2000 chest x-rays, and then we had machines generate these reports. We intermixed them and we showed the reports to attending physicians and asked them to assess the quality. Of course, they were blinded, so the clinicians did not know which report was produced by who, and they were asked to rate the quality using the ACR radiology read criteria. And if there was any missed findings, they cataloged those as well, and we asked them to give a qualitative score. The study was done in RSNA 2018 to get an initial level of performance and capabilities, based on which we modified our algorithms and upgraded with data sets and so on. So the final study that we did was at a symposium in which we had 3 famous radiologists. I think many of you may be familiar with them. Elliot Siegel, Curtis Langlotz, and Chuck Kahn. And they sat in separate reading rooms, dark rooms, and they were one of them was given machine generated, one of them was given radiologist generated, and one was given combined. But none of them were told who got what. And we were live observing what they were rating their reports by, and these curves were sort of going up. And then we finally revealed the results to the audience. And as you can see from here, here are the reports manually, and here are the reports. These are the radiology resident reports, and these are the automatically readed reports. And you can see that the statistical performance is similar, but also there's a little bit of an edge to the machine in the quality of the reports. There are more excellent quality reports, and the score ranges also show a skew in the higher range for them. Now, this was because of the experiment and because of the time limitation of it, we could only evaluate about 166 reports in the 1 hour time we gave the radiologist to do. So this is one of the caveats to see. So overall, to see I hope I gave you an indication of what does it take to do a grand challenge over multiple years of research, addressing a problem end to end, to think of a capability that is meant for practical clinical workflows, and honing the techniques to the level of sensitivity and specificity needed for clinical workflows. We are going through a commercialization phase of this technology, but if anyone is interested in learning more, I'll be happy to talk and point to relevant papers on this. So here are some publications from this work.
Thank you. Thank you, Dr. Syeda-Mahmood, for a very interesting talk. So if there are any questions, please type them into the chat or Q&A. Or really at this point, you could just unmute your microphone and ask the question. So I do have a question. It seems like the focus on chest X-rays is because how common that exam is and how much data there is available. Are there other places this technology could be translated to without a big burden?
Well, so some of the fallouts that came from there was, are there automated ways of building lexicons that would acture the findings much faster instead of spending years with clinicians trying to go? So that's one of the active research areas on the tech side. Similarly, the automated labeling methods are the scalable methodology. So I think going forward, this would be the standard approach that if the text analytics is reasonably good quality through verifications that you do. You can think of scalable ways to building models quickly for, since reports are available for pretty much all imaging, right? So whether you're talking about cardiology, radiology, neuro, and so on. So you're going to have reports. So, but to understand those reports, you need the associated lexicons or the vocabularies. Doing a totally machine learning approach, people are trying those as well. But right now, the comparison has always shown that the vocabulary-driven approaches beat them hands down because of just the knowledge that they incorporate. So if there is some way in which this technology could, take the next step in there, that would, so you can imagine in future, you won't take that long to build new models for new body parts or new anomalies because we have a scalable method. So that was one of the learnings from there, that we were able to label 500,000 images in a matter of 4-5 days, including verification.
Right,
Whereas we
that's an
spent
amazing amount of work. Wow.
yeah.
Yeah.
Yeah. So those are the things. The model building exercise, this is a whole image approach we took, which was one of, and I was expecting one of those questions is why not take a regional approach? This was a learning from us that when you have such large scale number of findings, the regional approaches are not going to work as well. And it is better to go with a more robust whole image approach. Relying on statistics from what is seen in typical reports to focus on which findings are important to call on, which are critical. And if you see the evaluation methodology for the Turing test, use the ACR review criteria, which are important to get some critical findings right. And if you don't report a non-urgent findings, it's okay. So we took hedge the bets on which findings are important to characterize and do well in those that are very prevalent. Also, we wanted to do well on those and those sort of things. So these are some engineering good ideas that you can incorporate with deep learning to do practical solutions in that space.
Okay, I don't see any more questions. So thank you again, Dr. Syeda-Mahmood, for an excellent talk.